In this video, I want to talk about the difference between space and space-time, because I think there could be some confusion there, even though we have gone through time dilation already, and you've seen this. But before we go forward into our next video, where we're going to discuss some other results of special relativity, we need to be clear on the difference between space and space-time. So to get right to it, when you look at this diagram as a whole, it represents space-time. That's 4 dimensions total, 3 dimensions of space and 1 dimension of time. And as a whole, that is what we call space-time. The space axis that you're looking at, which is when we talk about things moving through space, spaceships and stuff, that axis is the space axis that represents 3 dimensions. But then we add the 4th dimension of time, and that creates 4-dimensional space-time. So the diagram as a whole is 4 dimensions, which includes time. That's what Einstein did. Now, in the old days, we only had the 3 dimensions of space, which is the horizontal arrow axis. But when Einstein came along, he put the time axis on there along with Hermann Minkowski and created space-time. And that's what we're looking at on this diagram as a whole, is 4-dimensional space-time. The space axis only represents 3 dimensions. If you understand that, you could maybe skip the rest of this video and move on to the next one. Or stay in this video and just review some things that we've already been over, just to amplify them and to embed them in your brain more deeply. So, let's start out by taking a real simple example here. We have our graph again, and remember, this represents 3 dimensions of space, and this represents 1 dimension of time, and together they make space-time. Our speed, you and me, and everything else is moving through space-time at the speed of light. I'm saying 1.0, which is 100% the speed of light. And the speed of light is designated by the small letter c. The main point is that every single thing there is moves through space-time always at the speed of light. Never slower, never faster. That's the only speed anything can go in space-time. However, space itself, just the space axes, the 3-dimensional space, that's a different story, because in that case, we can only go up to the speed of light and accelerate to the speed of light. Remember, that's just space. We're not including time. So our motion through space can always be from 0 to almost the speed of light, but we can never get to or exceed the speed of light in space. So what I'm going to do here is try and explain a little bit more of that. Here we are. My red vector, you might remember from the previous videos, is laying on top of your vector. We are both moving through space-time at the speed of light. However, we're both at rest relative to each other, so we are just sitting at a table across from each other. We are both aging at the same rate. 1 second for you is 1 second for me. And like I said, we're moving through space-time, but you'll notice there is no space component. We are not moving through space at all relative to each other. We're just sitting across at the table. So that means our speed through time is a full 1.0 the speed of light. We're moving at the speed of light through time together. We're aging at the same rate. And our speed through space is 0. Let's take a look at another one, and this might help. As we increase the speed between ourselves, in other words, I'm going to get in a spaceship, and I am going to go at, in this case, 26% the speed of light through space. So you see me moving at 26% the speed of light through space. All right? Now, the way you get that is when you look at me in my spaceship, you see the projection of my spaceship on the space axis. My vector here, my space-time vector, my space-time speed has not changed. I'm still moving at the speed of light through space-time. But that speed of light has 2 components. One of them is my motion through space, shown here, and the other one is my motion through time, shown here. And if we combine those, we will get the length of this vector. But we have to be clear that this vector in space-time is always the speed of light, but in space alone, we are limited to less than the speed of light through just space. Because we're always moving at the speed of light through space-time, but it has a time component and a space component. So the faster I move through space, the slower I move through time. And so 1 second for you here is only 0.97 seconds for me. Let's look at another one. Here I'm going at 50% the speed of light. My vector rotated further. My spaceship is now going faster. I'm going at half the speed of light. And now 0.87 seconds on my clock is 1 second on your clock. So I'm not aging as fast as you. I'm still moving at the speed of light through space-time, but I'm only going at half the speed of light through space. Let's look at another. Again, you see the vector rotate further as I go faster. Now I'm at 71% the speed of light. I'm still moving through space. Through space, 71% the speed of light. That's the 3 dimensions of space. I am still moving at the speed of light through 4-dimensional space. My speed through time is now only 0.71, and so you've got a second that goes by on your watch, but only 0.7 seconds go by on mine. Again, now I'm going 87% the speed of light. The components of my vector and for my spaceship in space-time still show the speed of light fully. However, my space component is 87% the speed of light, and I'm only moving through time at half the speed of light now. So that means 1 second on your watch is a half a second on mine, or 1 second on my watch is 2 seconds on yours, or 1 year on my clock would be 2 years on yours. Let's go faster. Here we have me going at 97% the speed of light through space. All right. And now my speed through time is much, much less because we have to combine these using the Pythagorean theorem. We will or have covered that already. But in the end, the combination of these components dictates our speed through space-time, 4-dimensional space-time. We're always moving the speed of light. I know that I keep repeating that over and over, but it's very important. I'm trying to drill that in because in space, we can never get to the speed of light, and that will be discussed in the next video. But in space-time, we're always moving the speed of light, and that can cause some confusion. That's why I'm doing this video. So we can see that as I change speeds in my spaceship, you can see the vector, my space-time vector is rotating in 4-dimensional space, but in 3-dimensional space down here represented on the bottom, the speed that you perceive me moving at changes. I'm going to take one last thing here that's very interesting, and I'm going to show you here. This is a light beam. Light is different. Light does not have rest mass like we do. You can't weigh it on a scale or anything. It just goes at the speed of light all the time through space-time like we do, except for one thing. Light is trapped in space. It moves in 3 dimensions of space in vacuum at 186,000 miles per second. And like I said, it is trapped in that space. Light, the vector for light lies directly on the space axis. Its projection through time is 0. Light does not move through time. Time does not pass for a light beam. Light is stuck in space. And when I say light, I mean all electromagnetic energy from visible light to X-rays, to gamma rays, and then on the lower end of the spectrum, we got microwaves, radio waves, but anything that's an electromagnetic wave moving through a vacuum in space is trapped in space, and light does not age. So I think that's an interesting thing. It's always measured to be the speed of light, no matter who measures it or what. Now, there are some exceptions when you get into light moving through water and things like that, but that gets into more classical physics. We're not going to discuss that here. What I wanted to make clear here, and the takeaway from this video, is that we are always moving through space-time, which is 4-dimensional at the speed of light as represented by this red vector. But you'll notice that as I change my speed through space On the bottom, you can see that. My projection in space alone changes. So I'm trading off motion through time for motion through space. I hope that makes sense to everybody, because it's very important that space is only 3-dimensional and space-time is 4-dimensional. And that makes a difference, because in 4-dimensional space, we are always moving at the speed of light. And in 3-dimensional space, we are limited to below the speed of light for massive objects. And like I said, light is different. I am not going to keep repeating that anymore. I think that's drilled into everybody's head pretty good. Let's go to the next video where we can look at some more interesting relativistic effects involving special relativity and high-speed motion.